For centuries, scientists have been unraveling the mysteries of the quantum world. The behavior of atoms and subatomic particles has long defied our classical intuition. They teleport, tunnel through barriers, and exist in multiple states at once. But now, a new breakthrough has taken our understanding to an entirely new level. For the first time in history, scientists have witnessed atoms synchronizing in free space. This discovery is not just a technological marvel. It is a fundamental revelation about the way the universe works. But what does it mean for atoms to synchronize? Why is this phenomenon so groundbreaking? And how could this change our understanding of physics, time, and even the future of computing? To fully grasp the significance of this discovery, we need to start with the basics, the nature of synchronization and its role in the quantum world. Synchronization is a phenomenon found everywhere in nature. It's in the way fireflies flash in unison, how heart cells beat together, and even in the orbits of planets. But at the quantum level, synchronization takes on an entirely different meaning. Quantum synchronization refers to a scenario where atoms, despite being physically separate, move or oscillate in perfect unison. Unlike classical synchronization, which happens due to direct interactions like mechanical or electromagnetic forces, quantum synchronization occurs due to the strange and counterintuitive properties of quantum mechanics. In most cases, atoms require an external force to synchronize, such as being trapped in an optical lattice or confined in a Bose-Einstein condensate. But what makes this discovery so astonishing is that scientists have now observed atoms synchronizing in free space, completely unconfined and free to move. This means that, under certain conditions, quantum systems can spontaneously align their behavior without any direct interactions, hinting at a deeper level of quantum connectivity than previously imagined. To understand how this discovery was made, we need to look at the experiment itself. Scientists began by cooling a group of atoms to near absolute zero, where quantum effects become dominant. They then used ultra-precise lasers to control and measure their states. What they observed was stunning. Despite having no physical connection and no external force acting to synchronize them, the atoms began oscillating in perfect harmony. This was the first direct evidence of quantum synchronization occurring spontaneously in free space. It was as if the atoms were communicating through an invisible quantum link, aligning their movements in a way that defies classical physics. The implications of this discovery are profound. It suggests that quantum systems may be far more interconnected than we ever suspected. It also raises the possibility that synchronization plays a hidden role in the foundation of quantum mechanics itself. But how is this possible? How can atoms synchronize without direct interaction? One possible explanation lies in quantum entanglement, one of the most bizarre and mysterious phenomena in physics. When two particles become entangled, their states remain linked no matter how far apart they are. Changing one instantly affects the other, even if they are light years away. Scientists suspect that the observed synchronization in free space may be an emergent effect of entanglement. If the atoms were subtly entangled before the experiment began, their synchronization could be a manifestation of this hidden connection. This idea aligns with recent research suggesting that entanglement is not just a feature of quantum mechanics, but the very foundation of spacetime itself. If entanglement can influence the behavior of atoms even when they are free-floating, it could mean that all particles in the universe are connected in ways we don't yet fully understand. One of the most immediate applications of this discovery is in the development of quantum clocks. Today's most precise atomic clocks use synchronized oscillations of atoms to measure time with incredible accuracy. But these clocks rely on carefully controlled environments, such as optical lattices, to maintain their synchronization. The discovery that atoms can synchronize in free space suggests that future quantum clocks could be even more precise and robust, requiring fewer constraints to maintain their accuracy. This could revolutionize fields like global positioning, satellite synchronization, and even deep space navigation, where precise timekeeping is crucial. But the implications go even deeper. One of the biggest challenges in quantum computing is maintaining coherence among qubits. Quantum computers rely on superposition and entanglement, but as systems grow larger, it becomes increasingly difficult to keep qubits synchronized. The discovery that atoms can synchronize in free space opens up new possibilities for designing quantum processors. If we can harness this natural synchronization, we may be able to build more stable and scalable quantum computers, bringing us closer to achieving practical quantum supremacy. This could lead to breakthroughs in artificial intelligence, cryptography, and simulations of complex physical systems. Beyond its technological applications, this discovery raises profound questions about the nature of reality itself. Synchronization in free space suggests that quantum systems may be governed by hidden connections that transcend classical physics. Could this mean that the universe operates on a deeper level of order than we previously imagined? Some physicists speculate that quantum synchronization could be linked to theories of emergent spacetime, where reality itself arises from the complex interplay of quantum information. This could mean that our perception of time, causality, and even consciousness is deeply rooted in the fundamental principles of quantum mechanics. Scientists are now racing to explore the full implications of this breakthrough. The next steps will involve testing whether this synchronization effect can occur at larger scales, beyond just a few atoms. If larger quantum systems can synchronize in free space, it could provide new insights into the unification of quantum mechanics and general relativity. Some researchers even speculate that synchronization might play a role in cosmic structures, influencing everything from the formation of galaxies to the behavior of dark matter. Could it be that synchronization is a fundamental principle of the universe, governing not just atoms, but the very fabric of spacetime itself? While the observation of atoms synchronizing in free space is already groundbreaking, the true significance of this discovery is just beginning to be understood. This phenomenon challenges some of our most fundamental assumptions about the behavior of quantum systems, potentially reshaping entire fields of physics. To fully appreciate the depth of this breakthrough, we must explore its broader implications, how it ties into quantum mechanics, space-time theories, potential technological applications, and even philosophical questions about the nature of reality itself. The study of synchronization is not new. Mathematicians and physicists have explored synchronization in classical systems for centuries, from pendulum clocks to planetary orbits. One of the most famous mathematical models describing synchronization is the Kuramoto model, which explains how coupled oscillators, such as fireflies blinking in sync or human heart cells beating together, can spontaneously fall into rhythm. However, in the quantum realm, synchronization follows an entirely different set of rules. The mathematical description of quantum synchronization requires incorporating the principles of superposition, entanglement, and non-locality. Physicists are now refining quantum versions of classical synchronization models to better understand the behavior of free-floating synchronized atoms. These models suggest that synchronization might be a fundamental aspect of quantum mechanics rather than a rare or isolated occurrence. Another fascinating aspect of this discovery is its connection to quantum phase transitions. In classical physics, phase transitions occur when a system changes states, like water turning into ice. In the quantum world, phase transitions occur due to changes in quantum states. A well-known example is the transition from a normal atomic state to a Bose-Einstein condensate, where atoms lose their individual identities and behave as a single unified quantum entity. Quantum synchronization might represent a new kind of phase transition, one that occurs in free space rather than in confined environments. If so, it could reveal new states of matter that exist purely due to quantum mechanical effects. One of the biggest questions arising from this discovery is whether synchronization in free space is limited to small atomic systems or if it could occur on much larger scales. If synchronization extends beyond a few atoms, it could suggest that the universe itself operates on a fundamentally synchronized framework. Some researchers are now investigating whether entire quantum fields or even macroscopic objects can exhibit synchronization under the right conditions. If this turns out to be true, it could revolutionize our understanding of quantum mechanics bringing us closer to solving some of the biggest mysteries in physics. Time is one of the most enigmatic aspects of physics. While the laws of physics generally treat time as symmetric, meaning that processes should be able to run forward or backward, our everyday experience tells a different story. Time always seems to move forward. Some physicists believe that quantum synchronization could provide new insights into the nature of time itself. If atoms can synchronize spontaneously in free space, could this be linked to the underlying structure of time? Could the synchronization of quantum states provide a clue about why time moves forward rather than backward? Some researchers propose that quantum synchronization may be connected to entropy, the measure of disorder in a system. If synchronization reduces entropy in a localized way, it might offer an explanation for how time emerges at a fundamental level. Perhaps the most profound implication of quantum synchronization in free space is its potential connection to space-time itself. In recent years, some physicists have proposed that space-time is not a continuous fabric, as Einstein's theory of general relativity suggests, but instead emerges from deeper quantum interactions. Quantum entanglement, for example, has been linked to the structure of space-time through theories like ER equals EPR, which suggests that wormholes and entanglement are two sides of the same coin. Could quantum synchronization be another piece of this puzzle? If atoms can spontaneously synchronize in free space, it might mean that the fabric of reality is woven together through hidden quantum interactions that transcend classical physics. This could bring us closer to a theory of quantum gravity, the long-sought unification of Einstein's relativity and quantum mechanics. One of the most unexpected areas where quantum synchronization might have profound implications is biology. Recent research has suggested that biological systems, such as photosynthesis in plants and the navigation abilities of birds, may rely on quantum coherence, where particles remain in a shared quantum state across large distances. If quantum synchronization occurs in free space, it raises an intriguing possibility. Could biological organisms be tapping into this effect to coordinate their internal quantum processes? For example, could human brain activity involve a form of quantum synchronization that allows neurons to communicate instantaneously? While this idea is still speculative, it is being actively explored by researchers in the emerging field of quantum biology. If confirmed, it could redefine our understanding of life itself. While the discovery of quantum synchronization in free space is primarily a fundamental physics breakthrough, it also has potential applications in cutting-edge technologies. 1. Next-generation quantum sensors. Quantum sensors rely on the delicate behavior of quantum states to detect tiny changes in physical conditions. The ability to synchronize atoms in free space could lead to more precise sensors for detecting gravitational waves, mapping underground structures, or even searching for dark matter. 2. Ultra-stable atomic clocks. As mentioned earlier, quantum synchronization could significantly improve atomic clocks. This could enhance global navigation systems, enable better synchronization of financial transactions, and improve the accuracy of scientific experiments that require precise timekeeping. 3. Quantum communication networks. One of the biggest challenges in building quantum communication networks is maintaining coherence over long distances. If quantum synchronization can be harnessed, it could provide a new way to establish reliable quantum communication links across vast distances, possibly even enabling interstellar quantum messaging. 4th, advanced quantum computing architectures. The stability and coherence of qubits are critical for building practical quantum computers. Quantum synchronization in free space might provide new techniques for maintaining coherence across larger quantum processors, leading to more scalable and fault-tolerant quantum computing architectures. The discovery of quantum synchronization in free space marks the beginning of a new era in quantum physics. But many questions remain unanswered. What are the exact mechanisms that allow atoms to synchronize in free space? Can larger systems, such as molecules or macroscopic objects, exhibit this phenomenon? Does quantum synchronization play a fundamental role in the nature of spacetime? Could this discovery lead to new physics beyond the standard model? Scientists are now designing follow-up experiments to explore these questions, using even more advanced techniques such as superconducting qubits, quantum optics, and artificial intelligence-driven quantum simulations. Some researchers believe that within the next decade, we may uncover deeper principles governing quantum synchronization, principles that could revolutionize our understanding of the universe. Quantum synchronization in free space is more than just a remarkable scientific discovery. It is a glimpse into a hidden order that may underlie the fabric of reality itself. It challenges our understanding of quantum mechanics, offers new pathways for technological innovation, and raises profound philosophical questions about the nature of existence.